Before we go any further, and without getting into a full programming tutorial, let me explain some of the concepts behind Objective-C, the language you use to program your iPhone and iPad app. Albert Einstein once said that technological change is like an axe in the hands of a pathological criminal. Often a little change or bug fix in one part of your program can have a disastrous impact on the rest of it. I can remember a fellow programmer once lamenting, "But I only changed one line of code," after making changes to a program and then putting it into production without adequate testing, only to have it take down an entire system complex. To minimize the side effects of only changing one line of code, you need to divide your programs into modules so that a change you make in one module won't have an impact on the rest of your code. I refer to this not rocking the boat aspect of good design as transparency. A module is simply a self-contained or independent unit that can be combined with other units to get the job done. Modules are the solution to a rather knotty problem. Even a simple program can run into hundreds of lines of instructions, and you need a way to break them into parts to make them understandable. But more importantly, you want to use modules because they make programs easier to modify. The idea of dividing your program into modules is as old as programming itself. The programming style or paradigm of a particular programming language dictates the way that you do that. Functions, or things like functions, have historically been the basis of modularization. This way of dividing things into modules is used in the programming style or paradigm known as procedural programming. Here's an example of procedural programming. The procedure starts, the alarm rings. If you're not ready to get up, you hit the snooze button, and there's a delay, and the alarm rings again. If you are ready to get up, you climb out of bed, and that's the end of the procedure. Functions in a procedural program are like the command and control structure of a large corporation or an army. Each module follows a very specific process, and each module depends on the other modules to finish before they start. In the last few years, however, the procedural paradigm has pretty much been supplanted, at least for commercial applications, by the object-oriented programming paradigm. In Objective-C, objects are the way a program is divided up. In an object-oriented program, you can think of objects as working as a team necessary to reach a goal. Objective-C is an object-oriented programming language, which means that it was created to support this kind of programming. You can find different styles, but unless you're a dyed-in-the-wool member of a particular camp, it's really unnecessary to get into that discussion now. Objective-C has its fans and its detractors, but my advice is to ignore both sides and get on with your development. The best object-oriented programs have their objects work like a team, with everyone playing his or her role and doing his or her part, rather than submitting to the traditional hierarchical command and control structure, where someone is in charge and tells everyone else what to do. As you might guess, object-oriented programs are built around objects. Look around right now and you'll find many examples of real-world objects. Your pet, your desk, your television set, your bicycle. Real-world objects share two characteristics. They all have state and behavior. Dogs have a state, such as name, color, breed, or whether it's hungry, and a behavior, such as barking, fetching, and wagging tails. Bicycles also have a state, such as the current gear, the current pedal cadence, and the current speed. And bicycles have behavior, changing gears, changing pedal cadence, and applying brakes. Identifying the state and behavior for real-world objects is a great way to begin thinking in terms of object-oriented programming. Real-world objects vary in complexity. Your desktop lamp may have only two possible states, on and off, and maybe two possible behaviors, turn on and turn off. But your desktop radio might have additional states, such as on, off, current volume, current station, and different behaviors, such as turn on, turn off, increase the volume, decrease the volume, seek, scan, and tune. Software objects are conceptually similar to real-world objects. They too consist of state and related behavior. In Objective-C, an object stores its state in variables and exposes its behavior through methods. Methods operate on an object's internal state and serve as the primary mechanism for object-to-object communication. An object brings together the data structure and the methods that process the data in the structure. Each object is like an independent machine with a distinct role and is capable of receiving messages, processing data, and sending messages to other objects. Hiding the internal state and requiring all action to be performed through an object's methods is known as encapsulation. This is a fundamental principle of object-oriented programming. Consider the bicycle example. By attributing state, such as the current speed of 20 miles per hour, the current pedal cadence of 90 RPM, and the current gear, which would be fifth gear, and then providing methods for changing that state, the object remains in control of how the outside world is allowed to use it. For example, if the bicycle only has 6 gears, a method to change gears could reject any value that is less than 1 or greater than 6. The idea is to keep your objects as ignorant as possible about the environment in which they work and the other objects they use. An object hides all the details of how it works, while allowing other objects to use its methods. Encapsulation makes it easier to enhance or extend an object's capabilities without disturbing how other objects use it. Although some dependency always exists whenever one object uses another, you limit those dependencies to do what other objects do rather than how they do it, and limit the number of objects each one uses. For example, many people have no idea how a computer works, but can effectively browse the internet, create documents, and receive and send email. Most people who can successfully drive cars have no idea how the engine works. I refer to this as the I don't care and please don't tell me approach. In fact, Sergeant Schultz of the famous TV show Hogan's Heroes captured the spirit of object-oriented programming with his trademark line, "I hear nothing, I see nothing, I know nothing." This is encapsulation. An object-oriented program consists of a network of interconnected objects, essentially modules that call upon each other to solve a part of the puzzle. The objects work like a team. Each object has a specific role to play in the overall design of the program and is able to communicate with other objects. Objects communicate requests to other objects to do something using messages. Object-oriented programmers think about objects as actors and talk about them that way. Objects have responsibilities. You ask them to do things, they decide what to do, and they behave a certain way. You do this even with, for instance, a sandwich object or a shape object. You can, for example, tell a sandwich in an object-oriented program to go cut itself in half, or tell a shape to draw itself. The resemblance to real things gives objects much of their power and appeal. You can use them not only to represent things in the real world, such as a person, an airplane reservation, or a credit card transaction, but also to represent things in a computer, such as a window, a button, or a slider. But what gives object-oriented programming its power is that the way objects are defined and the way they interact with each other make it relatively easy to accomplish the goals of extensibility and enhanceability. That is, achieve the transparency that is a hallmark of a good program. You can accomplish that by using 2 features that are the bedrock of object-oriented programming languages: encapsulation and polymorphism. As I said before, encapsulation means hiding the internal mechanisms and data structures of a software component behind a defined interface in such a way that users of the component, other pieces of software, only need to know what the component does and don't have to make themselves dependent on the details of how the component does what it promises to do. This means that the internal mechanisms of a module can be improved without having to make any changes in any of the modules that use it. It also means that the component is protected from user meddling, like trying to rewire a heater. And things are less complex because the interdependencies between modules have been reduced as much as possible. Again, this is the way modules or objects should work in an object-oriented program. You want the objects to limit their knowledge of other objects to what those objects can do. That way, if you change something, you don't have to go digging through a zillion lines of code to figure out whether any code in your program is dependent on something being done a particular way, and then changing that dependent code to work with the new way. Ignorance is bliss. I hear nothing, I see nothing, I know nothing. Encapsulation makes possible the ability to change how an object carries out its responsibilities or how it behaves, which is enhanceability. It also makes possible the ability to add new responsibilities to an object, which is extensibility. One of the primary things that objects encapsulate is their data, and another thing they do transparently is add new objects. I've talked about encapsulation. Let me talk about the other feature that is the bedrock of object-oriented programming languages, and that is polymorphism. Polymorphism is about cultivating more of the same. Your friend's refrigerator is not the same as yours, but you know how to open it and find the beer. Different refrigerator models offer different features, but they operate the same way. Your objects shouldn't have to care about how one object is different from another as long as the object does what the requesting object needs it to do. I refer to this as the more of the same approach. This feature in object-oriented languages makes it possible to add new objects of the same type and have your program handle them without making any changes to the code that uses them. For example, you can create a program that processes cash and credit card transactions, and then sometime later you can add an ATM transaction and have the program process that new kind of transaction without having to make any changes to the processing logic. The capability of different objects to respond, each in its own way, to identical messages is called polymorphism. Although encapsulation allows you to ignore how things are done, polymorphism allows you to escape the specific details of differences between objects that do the same thing in different ways. In the real world, if you can drive a Chevy, you can drive a Caddy or any other car, as long as the controls are more or less the same. It isn't that a 1959 Cadillac and a 1958 Corvette are the same. If they were, what would be the point? What's important is that they are different, but you can go about using them the same way. In a program, different objects might perform the same methods in different ways. If the user spends cash, a cash transaction object subtracts that amount from the user's budget. If the user uses a credit card transaction will first have to convert the amount in foreign currency that the user charged to dollars and then subtract it from the budget. An object has responsibilities. Other objects ask it to do some action, such as draw a shape or make a transaction, and it decides what to do and behaves a certain way. The other objects don't meddle with the encapsulated details of how the action is accomplished, as long as the expected result occurs. They work as a team. Each object has a specific role to play in the overall design of the program and is able to communicate with other objects. So if an object needs to be modified, encapsulation ensures that the modifications don't interfere with existing code. Each object can also be replaced by a better, more functional object that does the same thing. Polymorphism ensures that it's possible to add new objects of the same type and have your program handle them without making any changes to the code that uses them. What makes this scenario work is the fact that with object-oriented programming, you can essentially copy all the characteristics of an existing class to make a new class. The new class inherits the methods and data structure of the existing class. Inheritance is the reason why you can replace an old refrigerator with a new one that not only does the same thing, but does it better. The new refrigerator inherits all the best capabilities of the old one and improves on them, at least you hope it does. Now, when I use the word class, I'm talking about code that you write. And when I use the word object, I'm talking about behavior at runtime. Whereas a class is a structure that represents an object's type, an object is something that exists only in a computer's memory. An object is an instantiation of a class. Objective-C, like other object-oriented programming languages, permits you to base a new class definition on a class already defined. The base class is called a superclass, and the new class is its subclass. The subclass is defined only by its extension to its superclass. Everything else remains the same. Each new class that you define inherits the methods and instance variables of its superclass. For example, let's look at geometric shapes. Squares, circles, triangles, rectangles, pentagons, hexagons, and octagons are geometric shapes. The general object is the geometric shape. Most geometric shapes have area, perimeter, and color. Each shape has its own color. Each shape also has particular formulas to calculate its area and perimeter. An object can inherit the common state and behavior of a generic object. However, each object needs to define its own special and particular state and behavior. The object model for this sample could have a shape parent class and a derived class for each specific shape. That would be a shape superclass and specific shape subclasses. The shape superclass is the parent. The square, rectangle, and circle are derived subclasses that inherit from shape. The triangle connector in the diagram represents an is-a relationship, as in a rectangle is a shape, a square is a shape, and so on. Inheritance allows you to do a number of things that make your programs more extensible. In a subclass, you can make three kinds of changes to the methods inherited from a superclass. You can add new methods and instance variables, you can refine or extend the behavior of a method, and you can change the behavior of an inherited method. As a result, you can use a superclass's declaration, which is its list of methods, to define a modus operandi for all of its subclasses that they have to follow. When different classes implement similarly named methods, a program is better able to make use of polymorphism, adding new objects of the same type and having your program handle them without making any changes to the code that uses them. You can also reuse code. If classes have some things in common, but also differ in key ways, The common functionality can be put in a superclass that all classes can inherit. Inheritance makes code elegant and less repetitive. If we know that all shapes have color, should we program a color attribute for each shape? The answer is no. Would it be a better idea to create a shape class that has a color attribute and to make all the specialized subclass shapes inherit that color attribute? The answer is yes. Inheritance greatly simplifies your code, and you end up with a program that's a great deal easier to understand and extend. A class definition is like a structure definition in that it defines the data elements, which in the diagram here are called fields, but in Objective-C are called variables. The class definition is a template for an object. It declares the instance variables that become part of every object of that class and the methods that all objects of the class can use. Each object, which as you recall is an instance of a class, has memory allocated for its own set of variables, which are called instance variables. They store values particular to the instance. When you create an object from a class, you're essentially establishing an area out there in memory land that can hold the object's instance variables. But while every object has its own instance variables, all objects of that class share a single set of methods. Here's what inheritance enables you to do. It allows you to make your programs more extensible and enhanceable. You can extend the behavior of an existing object without impacting the existing code that already works. You can add new methods and instance variables. You can refine or extend the behavior of a method by adding a new version of the same method while continuing to use the code in the old method. You can change the behavior of a method you inherit. You do this by replacing an existing method with a new version, by overriding the old method. However, the old implementation is still used for the class that defined it and other classes that inherit it. Changing behavior is not unusual, although it does make your code harder to follow. One of the most important ways to use inheritance is to create a protocol. A protocol in this sense is a list of methods that subclasses are expected to implement, such as calculate area, calculate perimeter, which have to be in all objects that come from this shape of abstract shapes. The superclass, the abstract shape, might have skeletal versions of the methods with no real functionality, or it might implement partially functional versions that you use in the subclass methods. In either case, the superclass's declaration, or its list of methods, defines a protocol that all its subclasses must follow. So to recap, polymorphism is the ability of different object types to respond to the same message, each in its own way. Because each object can have its own version of a method, a program becomes easier to extend and enhance, because you don't have to change the message to add functionality. All you have to do is create a new subclass, and it responds to the same messages in its own way. Polymorphism also allows you to isolate code in the methods of different objects rather than gathering them in a single function that has to know all the possible cases. When a new case comes along, you won't have to recode everything. You need only add a new class with a new method, leaving well enough alone as far as the code that you've already written, tested, and debugged is concerned. This encapsulation and polymorphism solves the problem of the widespread impact that changing a data structure may have. Only an object's methods that are packaged with the data can access or modify that data, although an object can, and often does, make its data available to other objects through its methods.